Section 9. Nuclear Forces. What limits and determines an atom's mass? Chem Talk. The nucleus of an atom. Discovery of the neutron. The average atomic masses of some elements were known in Mendeleev's time, even though scientists didn't know much about the actual structure of an atom. In Part A of this Investigate, you explored the idea of how the atomic mass relates to the atomic number. Mendeleev began organizing his periodic table by listing all the known elements in order of atomic mass. However, he found that organizing the elements in this way did not always make sense in terms of the behavior of the elements. He concluded that his measurements of atomic mass were incorrect. In those situations, he used the properties of the elements to place them in the table. As it turned out, Mendeleev's measurements were not necessarily flawed. Although early models of the nucleus included the proton alone could not account for the fact that the mass of a helium atom is 4 times the mass of a hydrogen atom, while the electric charge on the helium nucleus is only twice that of the hydrogen atom. Lord Rutherford, after discovering that atoms had a nucleus, addressed this problem. He suggested that another particle was present in the nucleus with about the same mass as the proton but no electric charge. He named this subatomic particle the neutron. The English scientist James Chadwick confirmed the presence of this particle in 1932. He was awarded the Nobel Prize in Physics in 1935 for his discovery. This discovery added a great deal to the understanding of the nucleus of the atom. It did not, however, solve all the mysteries concerning the atomic masses of some elements. Scientists today refer to protons and neutrons as nucleons. They both reside in the nucleus and are almost identical in mass. The mass number tells you the average number of nucleons. The following table compares properties of the 3 major subatomic particles. And here are the 3 major subatomic particles. Isotopes. In Part A of this Investigate, you also investigated why the atomic mass of an element is not a whole number. Not all atoms of a given element have the same number of neutrons in the nucleus. Think about the chlorine twins and what do you see? Only the number of protons, the atomic number, only the number of protons, the atomic number, is the same in all atoms of a given element. Atoms of the same element with different number of neutrons in the nucleus are known as isotopes. Isotope implies same number of protons. Isotopes are identified by their mass number, the sum of the number of neutrons plus protons. You can refer to an element by its name, chlorine, by its atomic symbol, Cl, or by its atomic number, 17. So that's using chlorine as an example. All 3 identifications are equivalent and used interchangeably in chemistry. The same element can have a different number of neutrons in the nucleus. Chlorine, which must have 17 protons in the nucleus, can have 18 or 20 neutrons. Chlorine with 18 neutrons and chlorine with 20 neutrons are the two isotopes of chlorine? Electrostatic and nuclear forces. In part B of this investigate, you brought two positive strips near each other. They experienced a repulsive force. This was true for two negative strips as well. When a positive and a negative strip were brought close together, the force was attractive. As you have heard, opposites attract. Inside the nucleus, the protons are repelling one another. Every pair of protons has a repulsive force between them. The force is very large because the distances within the nucleus are very small. The nucleus is between 10,000 and 100,000 times smaller than the atom. As you saw in section 4, the electrical force can be described mathematically. Where F is the force, K is Coulomb's constant, a number equals 9 times 10 to the ninth power Newton meters squared divided by c squared. Q1 and Q2 are the charges, and d is the distance between the charges. As the distance between the charges increases, the force weakens. Since the distance in the denominator is squared, if the distance triples, the electrical force is 1/9. 1 divided by 3 squares. 1 divided by 3 squared, which equals 1/9 as strong. The question then becomes, what holds the protons together in the nucleus? The protons do have an electrical force pushing them apart. However, they have the larger nuclear force holding them together. The nuclear force is strong at short range. Anywhere beyond a distance of approximately 10 to the negative 14th meters, that's less than 1 10 millionth of 1 10 millionth of a meter. So they're referring to the very small distance of 10 to the negative 14th power. The nuclear force is 0. Neutrons in the nucleus are also attracted to each other and to protons with the nuclear force. Electrons are not affected by the nuclear force. Electrons belong to a different class of particles than protons and neutrons. They do not interact with the strong nuclear force. Again, electrons do not interact with the strong nuclear force that is contained in the nucleus of the atom. Properties of the 4 fundamental forces. Scientists recognize 4 fundamental forces that act throughout the universe. One of science's greatest challenges has been to try to discover relationships between the forces. Many scientists think that all 4 forces may actually be different aspects of a single force. The theory that would explain how all forces are related is called the grand unification theory. The force everybody is familiar with is the force of gravity. Gravity is the force of attraction between any two objects with mass. The greater the mass, the greater the attraction. This force can be observed by dropping a coin on the floor, where the large mass of the Earth makes the force very evident. The gravitational force can be described mathematically as force of gravity equals gravitational mass times distance over distance squared, where force where F subscript g is the force between the objects, g is the universal constant equal to 6.67 times 10 to the negative 11th Newton meters divided by kilograms squared. M1 and M2 are the masses up here, the masses of the objects. Mass of object 1, mass of object 2. D is the distance between their centers, so we have distance down here. The electromagnetic force is responsible for our sense of touch, holding materials together, and lightning. Almost all forces we experience can be traced to the electromagnetic force. During the 19th century, physicists showed that the electrical force and magnetic force actually are a single electromagnetic force. This force is much, much stronger than the gravitational force, but also decreases rapidly with distance. The other two fundamental forces are difficult to visualize, but they play critical roles in the nucleus of every atom. The strong nuclear force is the attraction between nucleons, protons and neutrons, and holds the nucleus together because it is a very strong force at a very close range. It is estimated to be about 100 times as strong as the electromagnetic force. However, it is a very short-range force. At distances greater than the size of a nucleus, the force is too small to measure. The fourth force is called the weak force. It plays a role in the radioactive decay of unstable atoms, particularly in the transition of a neutron to a proton. During the latter half of the 20th century, physicists were able to show that the electromagnetic force and the weak force were two aspects of the same force described as the electroweak force. The weak force has a range of about 1/1000th of the strong force. Types of forces: gravitational, electromagnetic, nuclear, weak. And this is the one that takes place inside the nucleus of the atom. Okay. Unstable atoms. Nuclei of atoms have a wide range of numbers of protons and neutrons. All possibilities do not occur in nature. For example, although you could probably assume that an element exists with 20 protons and 20 neutrons, you can also assume that no element exists with 50 protons and only 1 neutron. In addition, scientists have found that elements do not occur in nature with an atomic number greater than 92. In the lab, scientists have been able to create heavier elements up to 118 atomic number as of this writing, and continue to explore this area of nuclear chemistry. However, all of these artificial elements are unstable. 3 of the ways in which unstable nuclei decay are alpha, beta, and gamma emission. In alpha emission, the nucleus spits out a particle that has 2 neutrons and 2 protons. This is identical to the nucleus of helium. Its chemical symbol is 4/2 He, and it is referred to as an alpha particle. Alpha particles are what Rutherford used in his experiment. In beta emission, the nucleus spits out a high-speed electron. The electron was not residing in the nucleus. A neutron in the nucleus decayed into a proton and an electron, and the electron was ejected. The symbol for this high-speed electron is and it is referred to as a beta particle. In gamma emission, the nucleus spits out a packet of electromagnetic radiation. This does not change the atomic number or atomic mass of the element. The symbol for this emission is, and it is referred to as a gamma particle or gamma ray. Alpha, beta, and gamma emissions can be a health risk or a medical therapy. Radiation can harm both cancer cells and healthy cells. A thin sheet of material can usually block alpha particles. A thicker shield is required to block beta particles. An even thicker shield is required to block gamma particles. Radioactive decay of large numbers of nuclei occurs with incredible precision and can be used as clocks to date items. Understanding why certain elements are radioactive requires a deeper understanding of the structure of the nucleus. Scientists are still trying to fully understand the stability of elements. If the nucleus of an atom is too large, the protons on one side of the nucleus are too far away to attract the protons on the other side of the nucleus. The protons can still repel one another since the Coulomb electrostatic force is long range. The interaction between the repulsive electrostatic force and the attractive nuclear force is one determining factor of the maximum size of a nucleus. Within a star, the stability of an atom varies with the nucleus. Light elements become more stable as the atomic mass, the number of nucleons, increases. The most stable element is iron, atomic number 26, with an atomic mass of 56 AMU. Elements with larger atomic masses become less stable. In general, elements with nuclear mass much less than 56 AMU can combine to gain mass, become more stable, and give off energy. This process is called fusion. Elements with nuclear mass much greater than 56 AMU can break apart to lose mass, become more stable, and give off energy. This process is called fission. Fusion is the process of small nuclei combining to increase their mass. The best example of fusion processes is what occurs in the Sun and other stars. Theoretically, the fusion process is ideal for supplying safe energy because it releases very large amounts of energy without leaving much dangerous radioactive residue. However, it is very difficult to accomplish this on an industrial level at the present time. Scientists hope to figure out how to harness the energy of nuclear fusion in the future because it would be an excellent source of energy for society. The process of splitting an atom into smaller atoms is called fission. This is the process that is used to produce nuclear energy. It is used to power nuclear submarines and to produce electrical energy in nuclear power plants all over the world. Let me scroll up a little bit so that as I'm reading this, you can see this nuclear power plant. The energy given off upon nuclear fission can be determined according to the famous equation E equals mc squared, where m stands for mass, deflect, c is the speed of light. The energy is liberated in this process because the total mass of the reactants is not equal to that of the products. There is a very small loss of mass. Think of the process as one where a small amount of mass is converted into energy. Since the square of the speed of light is 9 times 10 to the 16th power meters squared divided by second per second squared, is a tremendously large number. A very small amount of mass can generate a huge amount of energy. So what they're saying is, because c is such a big number, even if you multiply it by a small number, it's still going to be big. And then what that does is, when you multiply these two numbers, it gives off a very large amount of energy. Okay, I'm going to scroll back down. It's a tremendously large number. A very small amount of mass can generate a huge amount of energy. The energy released in nuclear reactions can be millions of times greater than in chemical reactions. This energy is generated by the formation of different atoms from the original atoms. In chemical reactions, new arrangements of atoms can occur, but the atoms themselves are unchanged. At the end of World War II, the fission atomic bomb used at Nagasaki required only about 6 kilograms of plutonium-239 to create a chemical blast equivalent to 19 million kilograms of dynamite. So that's just using that very small amount, and it created this very large amount because of the multiplication. The use of nuclear energy for the production of electricity is apparent as you look at the numerous states that depend on nuclear energy. For example, over 40% of Illinois' electricity is produced by nuclear energy. That's right south of us on the state line. Nuclear fission does create some major problems. These include security, safety, radiation, removal of spent rods, and disposal of waste. The disposal of nuclear waste has its own particular set of problems, and probably the most important of these is the half-life of the byproducts of nuclear power generation. The fission process creates many radioactive isotopes, each emitting its own hazardous radiation at its own particular rate. The half-life of a radioactive isotope is the length of time it takes for half of any quantity of that isotope to decay. The unstable isotopes decay by emitting radiation. They do so until a stable isotope is formed. The stability of an isotope has to do with the ratio of protons to neutrons in the nucleus, and will not be discussed further here. Half-lives of isotopes can be as short as less than a second and as long as tens of thousands of years. The uranium-238 that is a radioactive byproduct of nuclear power production will decay through a series of other radioactive isotopes until a stable isotope is formed. The half-life of U-238 is 4.5 times 10 to the 9th power years. This means that it will take that many years for half of the U-238 to decay into Pp-206. The half-life of Kr-93, one of the many products of U-235 fission, is 1.3 s. For any radioactive material, after 2 half-lives, 1/4 of the original sample remains. After 4 half-lives, 1/16 of the original sample remains. Half-lives of Kr-93. Okay, so here's this table. With the problems facing nuclear energy and the problems of the United States, with the problems facing nuclear energy and the problems the United States continues to experience because of dependence on oil for energy, there is a need for continued research. Numerous universities Numerous universities and government facilities are trying to improve the efficiency of nuclear fission and, at the same time, trying to develop nuclear fission for commercial use. This ongoing research is expensive and depends on the government, industry, and other organizations for continued support. This research and the use of nuclear energy itself must be directed by a careful risk to benefit analysis. Nuclear radiation can be both extremely beneficial and extremely dangerous. It just depends on how you use it. Used as a medical tool, radiation has extended the lives of many cancer patients. This process is also important for generating electrical power. However, there are high costs in terms of waste disposal and other problems. If scientists can learn how to harness nuclear fusion, they can alleviate the nation's electrical problems while decreasing pollution. The field of nuclear science is going to continue to grow. The future will provide great opportunities for a student scientist like you to get involved. The most recent views of the nucleus reveal that the protons and neutrons within it have internal substructures. Experiments similar to the Rutherford scattering experiment in section 4 reveal this substructure. Theories have shown that two up quarks, each with a charge of positive 2 over 3, and one down quark with a charge of negative 1 over 3, each with a charge of positive 2/3 and one down quark with a charge of negative 1/3, combine to create a proton with a charge of positive 1. Similarly, one up quark and two down quarks combine to create a neuron with a charge of 0.